A modern Formula One pit stop operates as a hyper-synchronized industrial operation. 20 mechanics coordinate their movements to strip and replace 4 wheels, with every human action compressed into milliseconds. On lap 27 of the 2023 Qatar Grand Prix, McLaren's pit crew serviced Lando Norris's car in exactly 1.80 seconds. That flat 1.80-second stop broke Red Bull's 2019 mark of 1.82 seconds. The gaption of 0.02 seconds is notable primarily because McLaren achieved it under a new set of regulations specifically designed to slow pit stops down. This timeline tracks a 2.0-second pit stop under the FIA's 2021 safety directive. The rules enforce mandatory human reaction windows. Mechanics cannot signal a completed tire change faster than 0.15 seconds, and the gantry light cannot turn green in less than 0.20 seconds. These artificial delays can simulate The governing body imposed these mandatory minimums in response to a string of loose wheels and severe mechanic injuries occurring in the late 2010s, aiming to eliminate automated guesswork from the pit lane. By locking the reaction times, the FIA left teams with a highly restricted set of unregulated margins. The only remaining areas for optimization are removing the nut, swapping the tire, and rethreading the new nut. McLaren engineers focused entirely on compressing these specific physical actions, squeezing every millisecond out of the tire swap while complying with the mandatory delays. The 1.8-second mark represents a successful navigation of a highly restricted legal and safety framework, proving that engineering teams will always find ways to optimize around structural roadblocks. Compare that to the 1990s, where pit stops routinely stretched to 10 seconds. The car would sit completely stationary while mechanics attached a heavy pressurized hose to pump fuel into the tank. Because the fuel flow dictated the total time of the stop, tire changes were rarely the critical path. Mechanics could complete their work and stand clear, allowing for wide margins of human error without costing the driver any track position. The mechanical architecture of the cars reflected this priority. The side pods were heavily sculpted and reinforced, specifically to accommodate bulky fuel valves and manage the intense weight transfer of incoming fuel. This environment created the overcut strategy. A driver would run a lighter, low-fuel car to set blistering lap times, staying on track longer to leapfrog heavier rivals while they sat trapped in the pit box waiting for the pump. When the FAA banned refueling in 2010, the bottleneck instantly shifted. The limiting factor of a pit stop moved from the fuel hose directly to the wheel nut. The physical demands escalated as well. Modern F1 cars weigh nearly 800 kilograms, significantly heavier than their 1990s counterparts, requiring substantially higher torque from the pit lane tools to secure the massive wheels. Removing the refueling mask exposed the raw mechanics of the tire swap. Every millisecond of human hesitation and mechanical lag was suddenly open to direct, unforgiving competition. The primary architects of this modern pit lane speed operate far from the track. The Italian manufacturing company Dino Paoli supplies the wheel guns for nearly the entire F1 grid. This exploded view of a Dino Paoli wheel gun details the transition away from heavy industrial impact wrenches. The focal point of this redesign is the shuttle system, the switch that reverses the tool's direction from loosen to tighten. This relies on mechatronics, integrating electronics into physical systems to bypass human reflexes. A manual shuttle requires the mechanic to physically flip a switch, taking 80 milliseconds. The modern e-shuttle replaces that with an electronic solenoid firing in under 10 milliseconds. That electronic system allows the mechanic to pre-program the gun. The tool is already set to the tighten phase before the car has even fully stopped in the pit box. The tool also houses integrated telemetry. Reaching the exact required torque automatically fires a digital signal directly to the gantry lights overhead. That instant data transfer fully replaces the historical system, where a mechanic had to physically raise their hand to signal their corner was secure. Relying on this telemetry introduces a specific risk. An electronic glitch or a cross-threaded nut tricking the sensor can trigger a green light before the wheel is safely attached. By integrating the e-shuttle, Dino Paoli removed the human brain from the decision-making loop of the tool. The mechanic no longer calculates when the job is done. The wrench operates as a digital sensor. Stripping away the mechanical delay leaves the biological limit. A standard human visual motor response takes approximately 250 milliseconds. To achieve a 1.8-second stop, mechanics cannot wait to see the car and then react. They must execute a pre-programmed open-loop motor routine, where the action begins before the visual confirmation. Using the car's entry telemetry, the mechanics begin their physical motions before the tires ever reach the painted lines, anticipating the exact 80 km/h approach. The 20-person crew is divided with strict kinematic purpose: 3 mechanics per wheel, 2 jack operators at the front and rear, and 2 individuals bracing the center of the car to prevent lateral shifting. The critical transition, pulling the exhausted tire off the hub and sliding the fresh rubber on, occurs in less than 0.5 seconds. This speed demands absolute precision from the driver. If the car stops a few centimeters long or short of the painted marks, the crew's pre-programmed physical routine breaks down entirely. To maintain precision under stress, teams deploy biometric sensors during training to map the exact heart rate spikes and muscle fatigue levels of each mechanic. Total synchronization requires the crew to train as a single biological machine. They do not treat the arriving car as a visual cue to react to, but as an anticipated geometric event. This specific philosophy separates the current field from the Red Bull pit lane dynasty of 2019, an era defined by aggressive tool settings and a prioritization of peak speed. The absolute peak of that approach was Max Verstappen's 1.82-second stop at the 2019 Brazilian Grand Prix, a record the paddock assumed was untouchable. Red Bull's 2019 data reveals high variance. They regularly executed sub-2-second stops, but the aggressive approach yielded a higher frequency of mechanical failures compared to modern standards. In 2023, McLaren attacked the problem through compliance optimization. This bell curve chart maps out the difference in strategy. McLaren designed their biometric training specifically to maximize efficiency within the unregulated zones, resulting in a tightly clustered dataset with minimal deviation from their target times. Progress at this level is microscopic. In over 10 years of official monitoring, the outright pit stop record has advanced by only 0.12 seconds. McLaren's 1.80-second achievement in Qatar was the statistical anomaly of their dataset, a perfect repetition where 0 human variance occurred across 20 individuals. McLaren bypassed Red Bull's historical dominance by applying extreme mathematical precision within a rigid set of constraints, minimizing variance instead of chasing raw speed. The industry standard for evaluating this precision is the DHL Fastest Pit Stop Award, which measures crew performance across an entire season. Looking at this bar chart of the DHL standings, the system mirrors the driver championship. Crews earn 25 points for executing the fastest stop of a race, heavily rewarding consistent execution over isolated spikes in speed. A 1.8-second stop provides 0 competitive advantage if the subsequent stop results in a 5-second failure due to a sticky nut or a misaligned jack. The penalty for variance is severe. A single cross-threaded wheel nut can trap a car in the box, dismantling a 300-kilometer race strategy in less than 10 seconds. Because of this risk, the elite tier of the grid operates against a 2.2-second baseline. Teams aim for this specific window to guarantee a 99% mechanical success rate while completely avoiding the FIA's reaction time penalties. Professional pit crews evaluate their success by their ability to hit the safe, repeatable limits of physics without fail, rather than celebrating a broken record. The 1.80-second stop in Qatar represents the asymptotic limit of current Formula One regulations. Any further reductions in time are effectively blocked by the laws of physics and pneumatic pressure. Breaking into the 1.7-second range would require structural engineering overhauls, dictating a fundamental redesign of the wheel rims or a complete elimination of the mechanic through fully automated mechatronic interfaces. The 2021 Safety Directive acts as a permanent ceiling on the hardware. No matter how fast the tools spin or the humans move, the gantry light legally cannot turn green any faster. Yet, the 1.80-second flat pit stop proves a core reality of the sport. Faced with rules explicitly designed to slow the cars down, Formula One engineering will map the exact boundaries of the constraint and master them anyway.